Okay, so we'll take a look at our updated calendar. Today is February 11th. We had a snow day last class, so today is class number 7, which means that the project which was supposed to be due today is actually due on Wednesday. So hopefully, is that not true? I think it was originally due today, class number 8, but now it'll be due next class on Wednesday. And then it looks like our next quiz is Friday of this week, quiz number 2. All right, today we talk about a technique called integration by substitution, and next class, more on substitution. Just to give you a sense of how important this topic is, we spend 2 days on it. Any questions on the calendar? Okay, and then if you really wanted to get a jump start on things, project number 3 is going to be assigned on Wednesday, but I do have it up here, so you can just grab one if you want one. Let's go ahead and take a look at a quick announcement right here. Hampshire College Information Session is happening this coming Wednesday at noon here at GCC. So if you have any interest in possibly transferring to Hampshire, then you can go take a look at that in the Academic Advising Center conference room. All right. Next handout is this one. So like I said, I reprinted the calendar, so go ahead and grab one of those. And if you take a look at the back of the calendar, then you will see this thing. Remember I had said that there was a collection of derivatives that I assume people had memorized, but it turns out that I wasn't clear about my assumption. So here they are. This is a list of derivatives and some corresponding integrals that I want you guys to memorize. I'm still forming how we're going to have a quiz on this, so I don't have any dates, but we'll say within the next 2 weeks, you need to push all of that stuff into your brains. Now, if you didn't have any of it, that would be a lot to ask, but I'm assuming you already have a lot of it. So, so start working through, see if you can commit a lot of this to memory in the next 2 weeks. You'll find that there are a lot of shortcuts. For example, if you happen to know the derivative of inverse sine is this, then take a look at the derivative of inverse cosine. What's the only change? It's negative. So it's not, like some of these formulas have duplicates, but maybe with a negative sign, all right? And I will also say that there is one formula in here that will be foreign to you, but I'll leave it, it's like a Where's Waldo. See if you can find the one that you don't know. And then in terms of the quiz, here it is. I'm projecting for all to see the quiz that we're going to take on those derivatives. What is it? It's exactly the same piece of paper without the formulas written in, okay? I'm not going to change the order. I'm not changing how it looks. I just really want you to just straight memorize. No cheat sheet on this one. You are writing the cheat sheet from memory, okay? Sometime within the next 2 weeks or so, I'm going to ask you guys to do this for me. All right. So again, we are on, what page did we say? 29. All right, so we're going to jump into number 2. We're skipping over number 1 for right now. We'll go to Steve. Okay, so I wrote the first test. I don't know when the first test is. When is the first test? February 25th. Still a little ways away. I wrote it over the weekend. More than half of the test is just straight find the antiderivative of. All of those straight antiderivative ones rely on the topic that we're going to see today. Every single one of them relies on this topic. So number 3, we will go to Dawn. Okay, we're going to do number 4. Together, we're going to find the integral of x squared plus 1 to the 50th times 2x dx using this thing called the U Substitution Method. Now, I'll say that if you decide to write down any of the notes that I write down up on the board, you don't need to get them all. There's a step-by-step process on page 1 of this packet that we're going to go through together. So just try to look for big picture ideas here. All right, that integral right there, certainly more complicated than anything on the reference sheet on the back of the calendar. You're not going to find this on the back of the calendar. So what we're going to do is do a conversion. We're going to say, okay, maybe there was a chain rule that happened, and this was the result. Somebody chain ruled to take a derivative of something, and they got this. And so what I'm going to do is I'm going to let u equal the stuff in the parentheses. And oftentimes we do this substitution where you let u equal the stuff in the parentheses. Don't worry so much about why we're doing that at this stage. Next thing we're going to do is take a derivative. So what's the derivative of x squared plus 1? 2x. And you can write it like this. I'm not going to write it like this, but do you guys agree the derivative of u with respect to x is 2x? So instead what I'm going to do is essentially multiply both sides by that dx and just put it over on the other side. So I'm not going to write du dx, I'll write du and put the dx over on the other side with the multiplication. And then I'm going to take my original integral and I'm going to start substituting. I'm going to use the letter capital I for the integral that we start with, just so I don't have to rewrite it. Integral of, instead of x squared plus 1, what is it? What did we call x squared plus 1? We called it u. So I'm just going to put the u right there. But that x squared plus 1 had something physically attached to it that I cannot remove. What was attached to the x squared plus 1 is the 50th. So I'm going to put u to the 50th. Now I'm going to come over here and I'm going to underline in green everything in the original integral that isn't down here in blue yet. What haven't I replaced yet? I haven't replaced the dx. I haven't replaced the 2x. You guys agree? All of those pieces, out of any of them, none of them appear in here in blue. So my task is to try to find 2x dx inside of this equation right here. I have to try to build 2x dx. Now in this case, the work is already done for me, right? What is 2x dx? It's du. It's just the derivative of u. So here we're just going to substitute. This 2x dx is really just du. So there's no funny business happening. Everything in the original integral is replaced to get something in our equivalent integral at the bottom. And the good news is the integral of u to the 50th du is easy. It's actually one of our basic integrals. It's on the back of the calendar if you take a look at it. This is just our power rule. So what do we do with that power? Add one or subtract one? We're doing an antiderivative. We add 1 to the power, so we go u to the 50th divided by, add 1 to the power, u to the 51st divided by 51. What do you stamp at the end of every indefinite integral? Plus c. And then the last step, this problem was in terms of x. It's very strange to give a final answer with u's in it. We invented u to make it easier for us. Instead of u, what are we putting? X squared plus 1. Questions on that one? And again, you can check every single antiderivative by doing what to your answer? Check its derivative. And hopefully we get exactly what we started with. All right, let's do this. We're not going to write it out. But when you take a derivative of this answer right here, so 51 is just a constant. I'm just going to keep that there in my mind. What happens to this 51 when I take a derivative? I bring it down to the front, which right away cancels with the 51 that's been sitting there. What happens to the power? Becomes 50. So I've got x squared plus 1 to the 50. That's all of this. But then the chain rule says you got to multiply by the derivative of the stuff. What's the derivative of the stuff? 2x, which is exactly that thing that was underlined up there in green. Works. That's exactly the thing you can take the derivative of to get all of this. All right, we were really fortunate in this case that the thing that we underlined in green happened to be exactly du. That was just lucky. All right, let's try number 5. integral of cosine of 5x dx. Okay, first step, let u equal the stuff in the parentheses. So u is 5x. Go ahead and take a derivative of that. See if you can write the dx in the right spot in one shot. So what do we get here? 5 dx. Good. Always du equals, always dx at the end. All right, we're going to start to substitute now. This thing right here, the original integral equals. Again, all I want to do is get the u in there. What does u go in replace of? It's the 5x. So it's the integral of, there's a u there, but I can't unattach that u. What is the u physically part of? Is the cosine. You can't take it out of the cosine. So it's cosine of u. So we're writing down bare minimum, what do we need to write so that the u gets in there? And that's it. I don't write anything else. And now I'm going to underline in green anything that's in the original integral that isn't down here yet. It's just the dx, right? That's the only thing that I haven't substituted for. So my task is to take this equation right here and solve it for dx. Okay, that's not too hard. Yeah, we're going to divide by 5. So let's divide this equation by 5. So we get du over 5 is equal to dx. And so then instead of dx down here, what do we put? Du over 5. Other questions on how we decided to divide by 5? Okay, so let's take this integral now. I'm going to take any constants that I find and bring them out to the front. So what can I pull out? 5? 1/5, right? That 5 is on the bottom, so it stays on the bottom. And then I'm just going to copy down the rest of the integral, cosine of u du. And cosine of u, it's one of the very few things that we know. It's on your reference sheet. It's on the back of the calendar. It'll be in your minds at some point in the next 2 weeks because I'm going to quiz you on it. What is the integral of cosine? Is it sine or is it negative sine? It's sine. All right, got to be careful with the positives and the negatives. All right, so Todd remembers our stamp plus C. What did I forget? The 1/5, right? It doesn't go anywhere. 1/5 was just sitting there. And then the last step, instead of u, what can I replace u with? 5x, the very original thing that we did. We said let u equal 5x. Now we just go back. Technically, the 1/5 only affects the sign, but even if you thought of it as a distributive into the c, 1/5 of a constant is also just a constant. Yeah, good question. Okay, any questions on this one? All right, so so it turns out there is a kind of shorthand way to do this technique of U substitution, and I'm going to show it to you here, and I'll show it to you in future integrals. But I will implore you to not use the shorthand technique until you're really good at this. The only way that you're going to be able to use the shorthand thing and be accurate consistently is if you understand what's happening. It's not like a substitute for learning what's really going on. Once you understand what's really going on and you've done enough of these, you start to be able to do some of it in your head. So I'm going to see, what are we doing here? Yeah, so I'm going to do this one here. a kind of mental way. And anything that I write in blue is stuff that's in my brain, blue brain. I'm only thinking the stuff that I write in blue. So I see the cosine of 5x, and I think, okay, maybe u could just be 5x. So I'm going to write it here, but really that's something that I'm only doing in my mind. And then in my mind, I'm doing the same. Okay, so then the derivative is 5 dx. So far, so good. Now, I would have a hard time solving the equation, figuring out what's missing in the integral, solving the equation, and doing all the rest of this in my mind. So here's the trick. The trick is to take the original integral. I'll copy it right here. Integral cosine 5x dx. And the trick is to do this. So I'm going to write some stuff here. Separate this from the rest of it. So I'm going to write something down, and this is actually the only thing that I write when I do this U substitution in my mind. I'm going to say in my head, okay, here in blue, du is 5 dx. I know that I need a 5 to be part of this integral. So I'd really like to have a 5 there, right? Because then it looks like somebody did the chain rule. Their 5 is there because somebody did a chain rule. But I can't go around just putting 5s inside of the integral. What I just did is multiply the integral by 5. I'm going to multiply it right away by 1/5 as well. But I'm going to choose to put that 1/5 out in front. So I haven't cheated. I've multiplied by 5 and then right away by 1/5. So the net effect is multiplied by 1, which is allowed. But in my mind now, I can see this entire thing right here as being, oh, this is just cosine of u du. It's really this. Because I put that 5 in there, I know that the du absorbs that 5. And then once I've got it looking like it should with the 5 in there, I say, okay, the answer is then just 1/5, and then I can do my integral of cosine. The integral of cosine is sine. Okay, so the shorthand way, again, takes a lot of practice to really understand what's happening. I'll do it again on the next example, but it is possible to be able to do a lot of these things in your mind if you practice a lot. So down here at number 6, it says we're going to look at the U substitution walkthrough from the beginning of the packet. So I think this is page 2. You might have ripped this off in preparation for the quiz, and I see that my page 2 is gone. All right, so U substitutions on the left, there's the step-by-step method. On the right is the example problem that we're going to look at worked out. And again, you're going to bring this with you to tests and quizzes, so you'll have this with you. So this problem right here says find the integral of x squared times 3 plus 4x cubed to the 5th dx. It looks far more complicated than any integral that we've tackled so far. Okay, step number 1. We will go to Ashley. Can you read number 1 on the left? Okay, so one thing I had said is maybe try letting u equal the stuff in the parentheses. So in this case, 3 plus 4x cubed. Without the 5th power, it might be tempting to include the 5th power. Don't. It's just the stuff in the parentheses. All right, we'll go to Richard for number 2. Okay, so what's the derivative of 3 plus 4x cubed? 12x squared, and we've written it this way, right? We've got a du, we've got a dx. Okay, we're going to Josiah for number 3. Okay, so bare minimum, how do we get u into this? All right, I find my u, it's there. So that's u, but what else do I need to write? What's physically attached to that u? So the x squared and the dx are multiplication. I feel like multiplication is not as strong as what's attached to this thing, is the 5th power, right? It's in parentheses for a reason. It's in parentheses because it's all being raised to the 5th. So bare minimum, if I'm going to get my u here, it's not just u, it's u to the 5th. Okay, and then we're going to Ernie for 5. No, sorry, 4. Okay, what do I see in the original that isn't part of this u to the 5th? I see x squared, I see dx, everything else was the u to the 5th. Okay, then we'll go to 5. Andrew? Okay, so I'm looking at two things now. I'm looking at this equation, and I'm looking at what I underlined up in red. So the question is, can I build x squared dx from this du equation? Well, I'm going to underline it in red here. There's my x squared dx. What do I do to both sides to get that x squared dx by itself? Divide by the 12. Yeah. Okay, so then down here, x squared dx is du over 12. So we divided both sides by 12. We'll go back to Sam for number 6. Okay, so instead of just u to the 5th here, what goes next to it is the du over 12. So it's a straight substitution. We're just substituting the red underlined part for with du over 12. And now we have an integral that we can handle. U to the 5th du is one of our basic ones. Where can you move this 12? And outside, right? So you take the constant multiples out front, makes the integrals look better. And so that 1/12 is now out here. And then what's the integral of u to the 5th du? U to the 6th over 6. So there it is, u to the 6th over 6. The 1/12 is still sitting there. Push those constants together, that's where the 72 comes from. Stamp it with a plus c at the end. And then the very last step here, instead of u, what was u equal in this case? Yeah, it was that 3 plus 4x cubed. So you can see that the u right here has become 3 plus 4x cubed. And then, of course, you can always check your answer by taking a derivative. And if you take a derivative of this thing, you have to write it out. You'll see the chain rule, and I'd encourage you to take some derivatives just to double check why this is happening, why it's working. It should not be mysterious what we're doing if you check a couple of answers. All right, then we've got some hints for choosing u. Generally speaking, you let u equal the stuff in the parentheses, but sometimes there are two things in the parentheses. So here are some suggestions. You can let u equal the stuff in each of the following cases. We're not going to read through everything, but maybe have this in front of you as you're working on the group activity and as you're doing your homework. But we have seen a couple of these so far. We have seen, was it sine? No, it was cosine of stuff. Didn't we do cosine of 5x? That was one of the ones we did today. And what did we let u equal when we had cosine of 5x? The stuff, the 5x, right? Just now, we had some stuff to a power right up above. 3 plus 4x cubed to the 5th, right? Some stuff to the 5th. And then the other ones, yeah, we haven't seen any of the other ones yet, but we will. Okay, so let's come back here. And I'll go back to where we were, which I think is right here, page 30. Okay, so can we go to tacit for number 7 on page 30? Okay, thank you. And I've already fixed this for next time I teach the course, but change that W to a U. And let's go ahead and just look at maybe some choices for U that have potential. Almost all the time, U is the inside function. So in the first case, this is one that we've done already, but what can we let U equal? It's x squared plus 1. Don't include the power, just the stuff inside the function. And then what is the derivative? 2x dx, which is lovely because 2x dx is exactly what's sitting out in front. So I'll underline it here, I'll underline it here. That's going to work. All right, how about the next one? We haven't seen part B before. T to the 4th times the cube root of 3 minus 5t to the 5th. Again, we let u equal something on the inside. What's on the inside here? 3 minus 5t to the 5th. You don't include the square root, just the stuff inside. All to the 1/3. Yeah, so it's the same as the power idea. What's the derivative of that thing? 25t to the 4. pt, thank you. Okay, something very good just happened. If we underline everything in the original except for the u, then we're underlining the t to the 4th. We haven't dealt with that, and we also haven't dealt with the dt. But do you see t to the 4th dt in that last equation? Yeah, it's right there. So all we'll end up doing is dividing both sides by -25, and we've got it. It's going to work. So again, the basic idea, if you're trying to start to look ahead to see what choice of u might work, you let u equal something, you take a derivative, and you really hope that the derivative you just found looks an awful lot like everything that's missing from the original integral. You can deal with multiplying or dividing by a constant, but you really can't deal with anything else. Let's take a look at C. In part C, there's no parentheses. All I have is a quotient. And you can't, please, please, please don't just think you can take an antiderivative upstairs and a separate antiderivative downstairs. That never works. So we need another way. Well, seems like there's only two choices for u. You could either let u equal the top or the bottom. I mean, I don't. So let's see what happens if we let u equal the top. Don't write this down. What's the derivative? Just 1 dx. Does that look at all like the bottom, the other thing? No. Okay, let's try letting u equal the bottom. You can write this down. And I take a derivative. (2x plus 10 dx). Don't forget the parentheses. Does that look like the top? It looks an awful lot like the top. What can you do to make it look exactly like the top? You can factor out the 2. So kind of looking ahead a little bit, you factor that 2 out, you get exactly what's up there. So we're not going to do the whole process, but essentially, I'm going to put like a, not an equals, but it's essentially going to look like downstairs is the thing we called u. Upstairs turns out to be basically du. There will be a constant that we'll have to deal with, and that's okay. But it looks like a du over u, which is on our sheet. It's one of the few things. Sam. You're going to oftentimes let u equal the more complicated thing. So if you want to see that as a greater order, absolutely. What do you think when you see the integral of du over u? It's one of the few that we need to know. It's a natural log. That's it. Right? 1 over x came from ln of x. So that right there will become an ln. All right, how about part D? Looking to let u equal the inside function. What do you see as inside? Is the e to the 4x. And I'm just going to highlight that it's this e to the 4x, not the one in the front. The one in the front, I have no idea what to do with. I don't know why it's there. But I'm letting u equal the thing on the inside. And then I take a derivative. What's the derivative of e to the 4x? Yeah, so I'll write e to the 4x times 4 dx. And then we're going to play our underlining game. So in the original, I see sine of u, and everything else gets underlined, e to the 4x and dx. And can you find e to the 4x dx in the last equation? Yeah, it's right here. You're going to end up needing to divide by 4, but it's close enough. So that's going to work too. The sign isn't underlined because in the same way that, for example, this guy right here was u, but then it became u to the 50th. Like you can't have the u without the 50 because it's attached to it. So this integral, we didn't write it, but this integral would become sine of u. The u sign doesn't disappear. We just didn't write all the steps. So the sign is part of the bare minimum that we had to write down when bringing the u in. Okay, and then number 8. Where are we now? Can we go to Tiffany for 8? Yes. Okay, so let's try this one here. Integral of 2x times sine of x to the 4th dx. Okay, so we've seen integrals with sine in them before. What can we let u equal? X to the 4th, right? Still the stuff inside of the sign, inside the function. Take a derivative. And by the way, this is part of what makes U substitutions challenging, at least initially, is that in the same problem, we're taking a derivative and then in a little bit an antiderivative, right? Like the integral sign means antiderivative, so it seems a bit strange to be taking a derivative in the middle of this antiderivative problem. So let's start substituting. Original integral equals. Okay, how do I get my u in here? What's attached to the u is the sign. So I've got sine of u, and then we're going to underline. What's in the original that isn't in blue yet? The 2x and the dx. Right? You need to find 2x dx in this equation. Okay, we can do that. What can we divide both sides by to make 2x dx? How do I turn the 4 into a 2? Divide by 2. How do I turn x cubed into just x? Divide by x squared. No problem. Divide both sides by 2x squared. So du over 2x squared equals 2x dx. Okay, so then we come back and substitute. Instead of the underlined red 2x dx, what can I put? Du over 2x squared, this thing. And that integral right there is problematic because it has u's and it has x's. And it's so problematic, it indicates the end of the game. We're done. U substitution didn't work here. So we either try a different U or we try a completely new technique. You can't go any further. So again, if you've got u's and x's inside of your integral, it's not going to work. You stop and you try something different. And it's okay to stop and try something different. You're going to have a lot more roadblocks this semester taking antiderivatives than you did last semester taking derivatives. Finding antiderivatives, the expectation is that you're going to take some detours. You're going to make some false starts before you find the path that leads you to the answer. So it's okay to have some of these false starts. What I wanted to get across in this example is how you recognize you're at a dead end. It's something with u's and x's. It just doesn't work. That said, we'll have many new techniques to try. Right now, this is pretty much the only technique. So we'll have other avenues soon enough. That integral right there, I don't have any avenue that will solve it. I have no idea how to find an antiderivative of that one. Okay, and then we'll go to Garrett for number 9.
Sorry, you don't know how to solve that one?
Mm-mm.
Can a computer solve it?
Good question. Good question. Let's see what it says. Garrett, can you read number 9 while I'm doing this?
Finally, note that U substitution always first you don't succeed or not. Got it. So the integral.
Okay, thank you. All right, so what is it? I don't know how to type antiderivatives here, so I'll just ask it for integral of, what is it, 2x sine 2x sine of x to the 4. Integral of don't know what it's going to say. Yeah, so you can't cross over a vertical asymptote. Yeah, but this guy doesn't have those, right? Yeah. It turns out it's quite easy to make something up that doesn't have an antiderivative. It doesn't work the way derivatives did. For derivatives, you just, all right, there you go. I don't know why I didn't see it. So for derivatives, you just churn through and you follow the rules and you get your derivative. For antiderivatives, there's no guarantee that it came from something. No guarantee it came from a derivative. Okay, so apparently our integral is equal to the square root of pi over 2 times s of the square root of 2 over pi x squared. Don't forget the stamp, see the plus c at the end. But s is the Fresnel S integral. All right, that begs another question. I thought that was the sine integral, but maybe it's the same thing. Oh, there you go. So it's similar to maybe Ernie what you were saying. Yeah, so the Fresnel S integral apparently is given by this integral from 0 to x, so it's an area accumulation function of sine of pi t squared over 2. I like the t squared there because the one we had was x to the what power? 4th, which is really just x squared squared. So I can kind of imagine that it came from something like this. And what does it mean that we've defined this function? It means that the thing inside the integral here doesn't have an antiderivative. So let's just give a name to it so we can refer to it later. We're going to introduce a new function because we can't handle this one. Yeah. All right, good question. So let's come back here, and you guys have 30 minutes, just about 30 minutes, to do this no substitute for substitution. I think that's enough time to go through all of it and maybe come back and try some of the challenge ones. So let's see how far we can get.